All right, so today here we're looking at the physics classroom concept builder, specifically polarization. Now on this screen, I'm showing you here, this is a little bit different. This isn't the actual concept builder you'll go through, but all of the questions are on here. It's a little bit faster sometimes just to show it in this manner, but you'll see this in several different levels. You'll see something that's charged like this with the balloon. This is a conducting sphere, positive, a conducting sphere. Here's a negative. This is supposed to be maybe like a piece of styrofoam. This would represent some kind of pipe in, which would be a conductor. Same thing. Down here, you've got something charged that's an insulator. The charges are just sitting there. They can be negatives or positives. And then you've got a cola can here. This would represent something that's a conductor. All of these are actually identical situations in the sense that they start out with protons and electrons. So there's positives all over this to start with at the very beginning. There's positives and negatives. Sorry, this thing is being dumb. When you start out, they're kind of all over the place. All right, and I zoomed in here a little bit to try to help us with some of these graphics, but it's important to note that although this starts out and those positives are all over the place, when you get this negative force on it, this negative charged balloon, all of the electrons that are kind of all over the place here, they tend to be repelled, and so they'll tend to congregate on this side of the sphere. And what that does is that leaves a positive charge on this side of the sphere. So what that would actually look like would end up being something like this, where you end up with an area of positives on there, like you can see right here, and an area of negatives on there, like you can see right here. And that's because of this negative here is providing a repulsive force to those electrons. Positives never, ever, ever, ever move, and so they're just kind of there, and you get this region of positiveness, a positive charge on this edge of the sphere, and a region of negative edge on this side of the sphere. Now, it's important to note that overall, there's still the exact same number of protons and electrons. Note, it has not gained or lost electrons, so it's still electrically neutral. So the answer to this one would be electrically neutral, and then this process of things getting where there's positives on one side and then negatives on the other side is called polarized. So the correct answer for this one would be electrically neutral and polarized, and you'll notice the electrons would be pushing away. Now, if you were to touch right here, it would shock you, and in fact, later on down here, we'll have to address that, and electrons might come or go. But that concept right there is the same for all of these in these initial settings. This initial questions. One more quick thing to note when you're working on these, and this is what you would see on the polarization. You actually have to click here and click through the options. And right here would be the one I was talking about. You got to click through those options so that you can do it. And then you click check answer. Well, there we go. Yay! That next level, this is that middle level, the master level. It gives you a scenario, and it's more about particle flow and charge distribution. So you kind of have the same thing where you have a charged object here, and then you need to be thinking about the protons and electrons on all of these. Now, I will tell you, insulators, electrons are never ever allowed to move. But if you have a positive here, you can you can click through these options, and the basic principle is insulators don't allow electrons to move, conductors do, and like charges repel and opposites attract. So what you're going to go through here is This one would actually be the correct answer because you end up in this conductor here. You have a bunch of electrons being attracted to the positive charge here. That leaves missing electrons from over here, so you end up with a positive charge there. And you get the exact same effect. These positives here attract some negatives here, some electrons there, and then that leaves a vacancy of electrons, which leaves a positive charge there. Now, the graphics on here are showing you that there's more electrons right here as opposed to all the way over here. That's kind of demonstrate as distance increases, that overall force of attraction decreases. And you'll notice nothing is happening in the insulator. That's because it's unaffected. Electrons aren't free to move around. That's the first part of this. The second part is particle movement. It's worth noting you will never, ever, 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 ever see positives moving. Never, ever, ever should there ever be green on that. Did I make that clear enough? So on particle movement, you're always going to be looking for how are the electrons moving, and there aren't electrons coming from this side all the way over to here, but we are looking for electrons moving, and in fact this is the right one. They started on this edge of this conductor and moved over here, and then likewise they started on this edge here and moved over here. So this one would in fact be the correct answer. And then I'm just going to go ahead and jump to the wizard level, this third level. This actually gives you a little bit of a scenario. We can replay it. You'll notice a positive charge comes over to this conductor. Somebody, you can think of this as a grounding agent, a person comes over and touches it when that's held near. Now, what you want to think about is when a positive charge comes close to a conductor, you end up with a bunch of negatives are being attracted. Remember from the previous one, a bunch of negatives would be being attracted. So you'd end up with some negatives on this side. Now, of course, that would leave a positive region on this side. And if you touch that, although at the start, this total thing here is electrically neutral at the beginning, after that polarization effect has happened, where you end up with negatives here and positives here, when you come in and touch that, when this person comes in and touches that, there is a positive charge here. And in fact, electrons from that person's finger are going to be attracted to that positive area. So if we move down here, let's see if it'll let us click through these options. Yes, it will. Remember, green, never, ever, ever. Positives, never, ever, ever, ever. Never, ever, 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 ever move. So we know that it's never, ever a green one. But as we click through these options, and remember when we were up here, there was a positive region and electrons would go into that positive region. This would be what was happening. The truth is, when in this situation, the only place that electrons move is either from the finger into the can or in the can to the finger. And that depends on what charge is over here. Now, if this can is gaining electrons from the hand, it's gaining negatives, so its net charge would be negative. Yay. Now, let's see if it gives us another one here. This one is exactly the opposite. So in this case, the negative charge comes over. All of the negatives on board here would be repelled over to this side. So you would end up with the opposite effect. You would end up with a negative region here and a positive region here. So that when that hand comes in and touches it, you're in fact getting, there's excess negative charges. So negatives are going to go into that hand. So remember, if we click through this options, no, that's green. Protons never move. Electrons are not moving from the balloon into the can. No. Yes, remember there were extra negatives on board here, and so those are going into the hand. Now, if something loses negatives, well, now the positives outnumber the negatives, so you have a net positive charge. And in fact, that would be the correct answer on this one. Thank you. I hope this helps, and have a great day.